Welcome back, everyone. Today we're going to go over a bunch of definitions from graph theory, and we'll talk a little tiny bit about at least one important theorem. But we're going to go through, and you'll see these words coming up a lot throughout the rest of this section. So first of all, I want to define for some little v and big V, that is some vertex on a graph, what the degree of v is. And the degree of a vertex is just the number of edges containing it. If you look here at my poorly drawn Peterson graph so that I can point at it, the degree of every vertex here is 3. So if I look at this vertex 1 up here, I can see these 3 edges coming from it. I'll go ahead and give you another definition that we tend to use a lot, which is that if u and v are both vertices, then we say u and v are adjacent if this set uv is in the edge set. And every part of your brain should tell me I wrote the wrong symbol there, that I really meant as a subset, but I don't mean as a subset, because remember, the edge is a set of sets with 2 elements. And so we're saying 2 vertices are adjacent if there's an edge between them. So for example, 2 and 7 are adjacent in this graph. 10 and 8 are adjacent in this graph. 5 and 2 are none adjacent because there's not an edge from 5 to 2. That means you could also say, in fact, is maybe saying something more deep here than it should be, but the degree of v is the number of vertices adjacent to v. So if you go back to our Peterson graph example here, 1 has degree 3 either because I'm counting these 3 edges, or if you want to think in terms of vertices, because I'm counting 2, 5, and 6 are the 3 vertices that are adjacent to 1. Note a vertex is definitely not adjacent to itself. Okay. So I want to go ahead and say our theorem for the day, or I guess I'm going to call it a lemma. This is the handshaking lemma. And what the handshaking lemma says is that if you take the sum across all the vertices of a graph of the degree of that vertex, that the thing you get is 2 times the number of edges in the graph. And although this looks profound at first, it ends up being pretty easy to prove because both sides, the left and the right, count the same thing. Namely, if I think about it, every edge connects 2 vertices. And so I'm going to think here of an edge as actually sort of consisting of 2 pieces. It consists of the half of the edge that goes to that piece and the half of the edge that goes to that piece. So I'm just splitting it into a red piece and a blue piece, and every edge goes between exactly 2 points, so they all have sort of 2 halves in this fashion. And so how many of these half edges are there? Well, every edge has two half edges. So there's, on the one hand, clearly 2 times e, 2 times the size of e half edges. On the other hand, every half edge contributes 1 to the degree of exactly one vertex. Because, well, this vertex gets the red half edge, this vertex gets the blue half edge, and so if I sum over all the vertices, the number of half edges emanating from that vertex, then I, in fact, will get the same number that we just counted. I just counted it in a different way. Why is this called the handshaking lemma? Well, it's called the handshaking lemma because if you imagine that you have a room full of people, and some of those people shake hands with each other, then on the right-hand side, we have the number of handshakes that have taken place, counted by the number of people each person has shaken hands with, but then that's also this thing. Again, here I'm picturing that each edge corresponds to a handshake, and so here again, this is the person on the left gets a count for a handshake, and the person on the right gets a count for a handshake, but the edge itself is one handshake, so anyway, you get this, you get the idea here of this. So in the case of the Peterson graph, for example, we said last time there are 15 edges here. So there are 15 edges. Twice 15 is 30. So size of the edges set here is 15. On the other hand, if I were to take the sum across every vertex of the degree of that vertex, well, there are 10 vertices. And each of those vertices has degree 3, so I would get 30. And so, in fact, if I think about doing this to this graph, I would get 30 equals 30. 3 times 10 equals 2 times 15. Okay. Now, I think this lemma doesn't say anything super profound, but it does have a corollary that's pretty important, that's not always obvious, which is that if you take the sum across all the vertices of the degree of that vertex, this is an integer, but it in fact is always an even integer because we've written it as 2 times an integer. So this is a non-obvious fact that is a constraint on what we can make the various degrees of our vertices. Okay. Next, I want to talk about the notion of a walk. And so a walk is a list of vertices, v1, v2, v3, dot, dot, dot. And then we stop somewhere, so I'll say we stop at vl. But it's not just a list of vertices, it's a list of vertices where vi is adjacent to vi plus 1 for all I. So if you want to imagine an example here on the Peterson graph, I could start somewhere. Let's say I start at 9, and then I walk from 9 to somewhere following this path. So I'll go from 9 to 4, and then up to 5, and then we'll say over to 10, and then over to 8, and then over to 3, and then back to 4, and then we'll stop. Note, there's no restriction, if I'm just talking about a walk, about whether I repeat things. So in fact, I didn't do this, but I could go ahead and throw a 9 there. And then I actually now have both repeated this edge and both of these vertices, and that's perfectly fine. All right. So that's the idea of a walk. Now, there are 2 specific constraints that you might want to put on your walk. Uh, Namely, you might want to say that you never repeat edges. And if you want to say that you never repeat edges, then it's called a trail. This is a walk. Never repeats edges. Okay, so here, for example, you might do something like 1 to 2 to 3 to 4 to 5 to 10, and I haven't repeated any edges, but I could not go back to 5, for example. And likewise, a path, this is a walk that never repeats vertices. Okay. But there's one exception that I want to include, which is that it's allowed that I start and stop at the same place. Okay, and so here I'm using the notation from before. V1 is the first vertex in my walk, VL is the last one, so I'm allowed to go and repeat that. So for example, I could go around this circle, 1, 2, 3, 4, 5, and back to 1, and that's corresponding to this. This is both a trail and a path. So we'll end up talking about both of these flavors specifically, and we'll end up talking about a bunch of variations on these. So we'll talk about, for example, is there a trail that visits every edge? And so you might have heard of the Königsberg Bridge problem. We'll talk about that. Or you might have played these games when you were a youth, where they gave you some figure like this and asked if you could draw the house without picking up your pencil and without going over the lines. That will correspond to some sort of trail. And then we'll also ask questions about, like, is it possible to visit every vertex exactly once? So is it possible to have a path that includes every vertex? We'll talk about that kind of thing as we go along. Okay. Next, I want to talk about connected. So we call a graph connected if for all pairs U and V, in V with these not being equal, we have a walk from U to V. Okay. So, in other words, no matter what place I start and stop, no matter which two I pick, it's always possible to get from one to the other. So, for example, I chose 1 and 9. In my Peterson graph, I can go from 1 to 6 to 9. Or if I picked 1 and 3, I could go from 1 to 2 to 3, or 1 to 6 to 8 to 3. And so, in fact, just about every graph we've written down so far is connected. I believe the only graph we've written down that's not connected is the empty graph. So something like this, I believe I denoted last time by that. This is not connected. I can't get from here to here, for example. Let's see, so here is an interesting example. So we have been talking about stars, and they've popped up, so you might ask yourself, is this graph connected? Note, this is the graph with exactly these 6 vertices. So there's no vertices in the middle. And I want to make sure you can see for yourself that this graph is not connected. And it's not connected because if I start at this point, which I'll go ahead and circle in red, let's see where I can get. Well, I can get from this point to here, and then I can get from this point to here, and I can get from this point back to there. But in fact, there's no way, starting at any of these red points, I can get to any of the other points. Likewise, if I started at this blue point, I could get to this blue point over here and this blue point over here. But I could never get to any of the red points. So really, this is just a very misleading way to draw a graph that actually looks like this. Where I've got a red triangle and a blue triangle. So be careful about deciding by looking at a glance at a graph whether it's connected or not, because you might get tricked. Now, I want to note that actually, if I just took this 5-pointed star in the middle of the Peterson graph, this graph actually is connected. So that is, if I redraw this, if I redraw this as that, I can go 1, 2, 3, 4, 5. So I can go from all the points to all the other points because I just gave you a way to cycle around it. And so, in fact, actually, this graph is isomorphic to, or in other words, is a different way of rendering just this graph, where I would say, okay, where do I go from 1? I go from 1 to 2 to 3 to 4 to 5, and then back to 1. So this graph is actually the same as this graph. So you might ask, well, then why in the Peterson graph do we draw it this way instead of just drawing it this way? And the answer is, well, you're more than welcome to redraw the Peterson graph so that this is a pentagon rather than a star. But if you do that, then it tangles up all of the outside vertices, and then they get tangled up back into a star. And so no matter how you draw this, you end up with a bunch of crisscrossing lines like this. Okay. Okay, so next, I want to define a cycle. So a cycle is a path of length at least 1, or sorry, of length greater than 1, or I'll say greater than or equal to 3, in fact, which starts and ends at the same point. Remember, this word path here specifically means we don't repeat edges. So a cycle is a path from a point to itself that visits every other point at most once. So, for example, 1 to 2 to 3 to 4 to 5, back to 1, that's a cycle. Or the other way, 1 to 5 to 4 to 3 to 2 to 1, that's a cycle. Notice I jumped to length at least 3 because it's not possible to have a path of length 2 because that would mean the point was the point or whatever. Okay. So, in fact, actually, the smallest cycle that you can make is a triangle. And so that is a cycle of length 3. Okay. Now, you might remember we talked about something closely related to this. Namely, we talked about these cyclic graphs. And when we talked about cyclic graphs, we said, okay, the smallest number of vertices to have on your cyclic graph is 3, and that C3 was the triangle. So in fact, one way to think about what a path is, one way to think about what a cycle is a cycle is an embedded copy of one of the cyclic graphs. So again, if I want to give a cycle in, let's say, the Peterson graph, I could give an example of a cycle that goes, say, 1, 6, 8, 3, 2, 1. That's a cycle, and it's a cycle of length 5. Note I listed 6 numbers here, but the first and last are the same, so when we're talking about the length of a cycle, we usually only count, or really counting the edges. So it's 1, 2, 3, 4, 5 edges. Okay, so here's a cycle of length 5. Which, again, if you think about it, this is showing me that there's a pentagon buried in the Peterson graph. There are a great many pentagons embedded in the Peterson graph. Okay. We're almost nearing the end of this list of definitions. But last up, I want to define something that ends up being very important, especially in computer science applications to graphs, and that is a tree. And so a tree is a connected graph with no cycles. And so I'll note, by the way, that not everyone universally agrees that this word connected goes here, but for my purposes, I'm going to say that trees are always connected. And so what that means is that I can have a vertex, and then I have to be able to get to every other vertex. But then I can never connect any of these vertices to each other, because that would form a cycle. And so I end up with some picture that looks like this, so you can see why it might be called a tree. And so you can look something like a family tree, for example, is a tree where you end up with this kind of picture. But as soon as I connected, say, this point and that point, then it would no longer be a tree, because then it would end up being, or that would then make a cycle that I could loop around. Okay. Last up for this video, I wanted to talk just a tiny bit about what happens when you talk about a graph where the edges are directed. And so I'll go ahead and say that we're going to call that a digraph. Okay, and all that is that shorthand for directed graph. It's a graph where each edge has an orientation. Okay, an orientation is just a fancy math word for direction. So I'm saying that each edge goes from a point to a point. So, for example, if I wanted to go back to, let's say, our graph of a square, I could take something like this, and I'll just put arrows on there to indicate that that's the direction that edge goes. I want to add, this does allow me to do this. So to say, okay, there's actually two edges between these two vertices, one going each direction. Okay, but if you look back at the words we've said today, most of them you pretty much immediately know how you would define them. So if someone talks about a walk is then going to be a list of vertices, just like before. But the only difference is now when I'm going on my walk, I can only walk in the direction of the arrows. So I could not in a walk go from here to here, would have to go along the arrows. And so I could, for example, go on a walk from here to here to here to here, back to there, and that would be perfectly fine. Okay. The one word I wanted to mention that does not work the way you would hope it is the word connected. And so, in particular, if someone says a digraph is connected, they don't mean the thing you think they do. So, a digraph is connected if, and so I'll say if the graph, and so if the undirected, an undirected graph is just a graph, but I can say undirected to emphasize the fact that I don't care that it's directed. The undirected graph underlying it is connected. Okay, and so if I have a directed graph, I can always say, okay, well, let's just forget about all the arrows and just say, okay, now I'm going to just draw exactly the same graph, but with no arrows. Okay. Note when I do that, these two edges collapse and they just become one edge because, again, in a regular graph, I can only have one edge between two vertices. And so I'd get this. And so this graph, this digraph, for example, would be connected because the underlying graph is connected. Okay. Now, why is that not great? Well, here is an example of why that's not great. If I take this graph, this graph is connected. Okay, does that mean I can get from anywhere to anywhere? Well, no, definitely not, because if I start at the upper corner, there's literally nowhere I can go. Right? I can't go that way, I can't go that way. But the underlying regular graph is the square. So I warn you about this specifically because this is something that if you come across this in a data science course or a computer science course, they're going to use the word connected, and it's not going to mean the thing that you think it is. Okay. When someone wants to say there's actually a walk from every point to every point on a digraph, they call that strongly connected. Okay. And so this graph here is connected, but this is not strongly connected because it's not possible to go on a walk from every vertex to every other vertex. Okay, so we'll come across more examples of graphs and digraphs at a later point, but for now, we're going to call that good as far as defining the basic vocabulary we're going to use as we discuss graphs. But we're going to drop off there for now, and we'll pick up next time talking about planar graphs and our first of many Euler's theorems. But until next time, be well.